Welcome back, everyone. Today I am honored to be joined by my grandfather, Mr. Jim Crapuchettes. Thanks for joining me.
You're welcome.
So, quick introduction on you. So you were educated at Stanford back when they allowed and encouraged white guys at that
Yes.
college.
And when a degree meant something.
Yes. And you helped install the first computers there, correct? At that college?
No, some of them. I worked for a particular group in the electrical engineering department, and I worked on the computer that they bought for probably $50,000 that wouldn't do much of anything today.
Yeah. And then you worked at Hewlett Packard,
Yes,
otherwise
that's
known as
right,
HP,
yeah.
correct? Helping install software.
Well, yeah, I have written software for since about 1968. I first touched a computer in 1961. It was the size of a refrigerator, and probably didn't have as much power as the wristwatch I used to have before I got a smartwatch. Okay, so that was the first one, and then I've been using computers ever since 1968.
Yeah, and then you started your own businesses, and you worked at Tandem Computers,
Yes.
and built systems that ran like a ton of the world's ATMs.
And business transactions. What I've done most of my life, until the last series in the decades, was worked on what people think of as I/O devices. Otherwise, I worked on the lowest level software that made the hardware do their things, like disks and stuff like that. That's what I did for most of my career. And then I ended up doing several years of web programming.
Okay, so what's different about that software as opposed to like the software that you install on your computer?
Well, every computer today runs some sort of thing called an operating system. And below the operating system is the piece of software that actually talks to, let's say, a disk drive. And it needs to know how to talk to the disk drive. The operating system doesn't really care how to talk to the disk drive. It just talks to the disk driver, and the driver needs to figure out how to make that work. And that's the level that I worked at for most of my life.
Yeah. So is it simpler code or more complex than as a general rule?
Different. You have to know how the hardware actually works in order to program it. So I had a lot of experience working with the hardware itself, so I knew how the hardware worked in order to tell it how to do what wanted to be done.
Got it. So how does something like a hard drive work?
Well, actually, I didn't work on actual hard drives itself. I just did the software that talked to the hard drives. But the hard drives, these days, of course, we have things like flash drives and
SSDs and such, yeah.
SSDs, yeah, and they're very different from the old days. The first disk drive I ever touched was probably about this big and had probably less memory than in the processor of today's computers, and that was a big thing.
Yeah.
And then the next ones I worked on were 14-inch discs that had like 5 megabytes, which today is like nothing.
Yeah. So when you were installing the computer at Stanford, that's $50,000. It's the size of a refrigerator.
Well, actually, that by the time I got to Stanford, they were smaller, but still very expensive compared to anything. And the computers were small and slow by today's standards, and everything was programmed in assembly language because all of the languages that people use today didn't work on a computer that had a memory that was, like infinitesimal in today's standards.
Yeah.
So we counted bits, not
Individual
bytes.
bits.
We sometimes we used tricks in order to get things crammed into those little computers.
Huh. Wild. But what was inside those computers that made them so large?
Well, the first one that I worked on briefly as a freshman in college had vacuum tubes. And it didn't have a disc which was like this and spins around. It had a drum which was like this and spins around. And the drum was fairly heavy and was driven by a 2-speed washing machine motor. So if somebody turned off the AC power, you literally had to put your head to the cabinet and make sure that the drum had stopped spinning, because if you turned the AC power on, the motor would start in low speed and would drive the drum into the read-write heads, destroying everything. Everything. So that was not. You didn't want to do
wow.
that. But the ones that I worked on at Stanford for a number of years were early transistor radios, computers, and no integration as we have today.
Yeah.
So just individual transistors on circuit boards, and so the result is it was large and small.
So why'd they use a drum as opposed to a disc?
On the early one, because they didn't have discs. It wasn't until I was through with college, before I went to Stanford, that I worked at IBM for a summer, and that's where the disk drive was invented. So you realize that 4 years before that, I had touched my first computer, and nobody knew about disk drives.
Yeah.
So that was what the really early computers had just the strangest things. History is wonderful. What they tried to do with the technology they had, which wasn't very much.
Yeah. What was inside the drum?
No, it's not on the outside of it. On the outside of it was coated with iron oxide, and then if it's iron, you can magnetize it, which is the way the disk drives work also. You can magnetize it, and so as it's spinning around, you can put a magnetic field on individual bits, if you will, and change their state. And then when you want to read back, you sense the magnetic field of the individual bits. Okay, I don't know that you want to go further than that.
Yeah, that sounds wildly complicated.
Yes, it is.
Yeah.
It's amazing that it works, actually.
Yeah. How did they come up with that? Like, who
Beats
figured
me.
out?
Beats me.
Someone just decided, hey, what if we magnetize little iron bits?
Yes, that's correct.
Huh.
Maybe that'll work.
That's wild. So what has enabled computers to become so much smaller today, to the point where I'm...
Integrated circuits.
Okay.
That means that the first transistors were literally a little smaller than the tip of my little finger in a plastic package or a metal can, and that was a single transistor. So then they came up with the first, what they call them, integrated circuits, which was a piece of silicon that had several transistors etched into it, which is a complicated process. And that was the beginning of the process that gets us where we are today, which is where, the processor in my watch probably has close to 1 billion transistors in it. And, it fits inside here, along with all of the memory and everything else that is in the watch. So it's just each time it gets smaller, you could cram in more things, and that's the process that happened since the 1960s.
What is a transistor, and what does it do?
It's just
exactly?
a simple on-off switch in silicon. The idea is, the concept is very simple. It's just like a light switch. You want power to flow sometimes and not other times. And so how can you do that with electronically? And the transistor does it electronically to let current flow or not flow. And that's what it does.
Why silicon?
Well, that is very complicated, having to do with the physics of atoms. And silicon was a material that was good to use because of the way the physics of atoms works.
And so, because silicon's rather like plastic, correct?
No, it's sand.
Oh, it's sand, of course. So
Silicon. So basically, they take sand, that's what they start, and they melt it, and they get rid of any impurities, and then they melt it and get rid of impurities, and then they melt it and get rid of impurities. And what they want to end up with is 100% silicon with nothing else in it at all. Okay? And then they start from that, and they actually very carefully put impurities in to make the transistor. It's a complicated process.
yeah, so it's like glass a little bit, because it's similar to the process of making glass where you melt sand.
But it's very much more. Yeah, glass is a place to start, but then the real work begins.
Got it.
Okay, I mean I could go on, but yeah.
Yeah, I mean, if you want to, go ahead.
Well, so they take this slab of silicon, which they melt and melt and melt and take the impurities out, and they end up with what's called an ingot, which is something could be this long or this long. I'm not sure exactly, but today they're up to 8 inches in diameter, and then they slice that with a diamond saw into very thin wafers, probably about this thick. And then they put the individual wafers in a machine that covers the surface of the wafer with a photographic resist, as it's called, and then they shine light on it through a pattern, and which makes patterns on this, and then the patterns cause the photoresist to be able to be etched away, so that you end up with the pattern on top of it with this resist. It's like a mask. That's what it is. The mask sits on top, and then they start etching it to do other things in order to put the impurities back in that actually make the transistors. And today, I think it probably takes 11 passes through something like that to make a processor.
Wow. But it doesn't stay in 8-inch diameter, right? Because it has to fit into.
So when it's all done, then they slice them up into little squares because they replicate this pattern all over the surface.
Okay. And then what do they use to add impurities into it?
Some very bad chemicals.
Okay. Fantastic.
I mean, actually, when we lived in Silicon Valley, you could go by the plants that actually made them, and you could see the containers outside of the buildings with these noxious chemicals in them, and they were all marked up with, the bad signs like skull and crossbones and stuff like that.
Don't touch.
Don't mess with these.
Yeah. So is there a limit to how small they can get? Because at some point, You can only make transistors so small,
Yes,
correct?
there is a physical limit. And so, for instance, back into the 80s and 90s, they were adding more and more transistors to the processors. But it got to the point there was this little problem called heat. And, you don't want there to be so much heat that the heat in the silicon melts the silicon. That would be kind of a bad thing. Or, so the problem is processors kept getting faster and faster and faster, and the heat kept getting hotter and hotter and hotter. And so they decided that there was a limit, that there was a physical limit to how to get rid of the heat. And so instead of making the processors faster and faster, they decided, well, we'll put more of them on the silicon. So, for instance, my watch, I think, has 6 processors in it, which it uses, and your laptop may have 8 or 16 or whatever, okay? And so that was just how to get the heat out of the thing.
Okay. And so that's when it says like you have a 32-core GPU or CPU.
Yeah, CPU. That means that there are actually 32 of them sitting in there doing the work. And then the operating system has to decide who gets to do what.
Right. And so what's causing the heat is the transistors turning on and off rapidly,
and the problem
correct?
is that they're not perfect switches.
Ah.
Okay? So even when they're off, they let some electrons through, and those electrons not doing anything are generating heat. And so particularly when it goes from the on to the off situation is when most of the heat is generated. And, your laptop is switching billions of times per second for each of those processors. And if you think about that, and each of the processors has got 1 billion transistors in it, it doesn't require much heat from one transistor to kind of make the whole thing pretty hot.
Yeah. And that's why they've got such big fans.
Yes, that's right. Or heat sinks or whatever they have it.
Yeah.
How do we get rid of it so it doesn't melt itself?
Right. So they used to be actual physical switches, correct?
Let's say the first computer that I touched actually had vacuum tubes for the switchers.
What does that mean?
Well, you just need to have something where we're just, you have a wire and you say, oh, I have a wire, but I want to put a switch in it. And what does the switch do? The switch just goes, either connects or doesn't connect, okay?
Okay.
And so your light switches are perfect switches, if you will, because they're either completely on or they're completely off.
Right.
Electronic switches can't be perfect switches.
Because?
Okay. Because the materials are the way that they are. I mean, that's just the way it is. It's physics.
Okay. So they're not actually switching on and off, but they're being magnetized?
No. This time is actually switching on and off, making electrons flow or not flow. Okay, and what you want is when you have the switch off, you want to have not one single electron flow.
Right.
Okay,
Yep.
And when it's on, you want to have perfect flow with no resistance.
Right.
Okay, because the resistance means that it'll generate heat, and so the problem that we have is that when not only is on not perfect, but off isn't perfect. And when you go from the on to the off or off to on, you get even more heat.
Like when you turn on a light bulb, that's when it's like a flash of heat, basically.
Yeah, right. Yeah. So It's the problem is the analogy is not perfect. Okay.
Yeah.
Okay.
Yeah. So how do you go from chemicals that you are putting into this silicon to cause impurities? How does that create?
It's physics,
Okay.
and that's a longer story and more. I think probably less interesting that people would care to hear about.
No,
So-
I'm interested. So how is that actually happening?
Well, then you have to know that when you have this perfect silicon, all the atoms are aligned with each other in a perfect crystal. So you've seen a crystal. I mean, diamond is a crystal.
Right.
Okay. Okay. So in a perfect silicon, all of the atoms in the silicon are perfectly lined up, spaced in 3 dimensions from each other, all over
Right.
the place.
Yep.
Okay. But perfect silicon can't do anything.
Right.
So in order to make it do something, you have to put imperfections into the silicon.
So that it's not all the atoms are evenly spaced.
Yes, as a matter of fact, so you have some different atoms in there in the crystal lattice. And it's very complicated because if you have 2 switches on a piece of silicon, you don't want this one to affect that one.
Right.
Or the other way. So that means that you have to keep them from interacting with each other, which means you have to have an insulator in between them, which you see how this gets. So
There's a lot of
you're getting
parts.
smaller and smaller, and you've got to make sure that you don't have any electrons stray from one transistor to the other, and they're getting smaller and smaller. And yeah, right.
Where are the electrons coming from?
Battery.
Okay. Okay, so
or
it just
some power supply.
right. So the battery is
The
feeding
source of electrons.
Right, feeding electrons in the silicon that has impurities. So they make perfect silicon, correct?
Well, that's where you start.
Right, and then they put impurities into it.
Yes,
So
in
that
a
when
very carefully designed patterns.
Yes, so that when you put electrons through it, some things turn off and some things turn on.
Yeah, and that gets yes, and you realize what it means is that it doesn't do any good to have just 2 switches next to each other.
No.
You need to have a lot of switches, and they needed to be connected. Some of them connected to each other, and some insulated from each other.
Right.
Okay, and then you build circuits out of that, and from the circuits, you do things.
Okay. How do you get to the? How does the circuits do things?
Well, do you want to be an electrical engineer?
Probably not, but this is fascinating. Because
Well,
I've always wondered. Because I see computers and phones, and I always wonder, like, how the heck do these things work?
well, so when I started, I could see the individual transistors, and I could see the wires on the printed circuit board that connected the individual transistors. So I could, if you will, I could see the actual circuit because this transistor was connected to this transistor, and these two, and this was connected to those two.
Right.
And you see what
Yeah.
is. Now, the only way you can look at the circuits is with an electron microscope.
Right. So is the silicon actually, when you put the electrons through it, is it changing
No.
its physics?
No. It is the electric fields that do it. So, okay, so let me see if I can give you an example. Okay, lightning. Lightning is a brief, powerful flow of electrons.
Right.
Okay? The reason that you see it is because it superheats the air so the air glows. You don't see the electrons. You see the air, which got so hot that it radiates light. Okay. Okay.
Okay.
All right.
Got it.
So, okay, there you see. Okay, so that is electric, and as a matter of fact, the reason that lightning occurs is because there's a buildup of electrons in the clouds, and when it gets so high, the electric field gets so high that the air can't act as an insulator.
Aha. And
Okay, so when so the field gets so high, and so the issue is an electric field, and the electric field gets so high that it just pushes electrons right through the insulating air
into
and you
its
get
conductor,
lightning.
into its natural, because it's always trying to go
so
to the
the
earth.
electrons want to say, I've got too many electrons up here. I'm going to make the electrons go to down there.
Transfer them, right?
Yes.
And eventually, the air is not enough of an.
Yes,
Okay.
and so for a while, the air is good enough insulator to keep the electrons up there in the cloud, but it gets to a point that there are so many up here in the cloud that it just wants to go, and so that's electric field. Okay.
Okay, so like a gathering of electrons, almost.
A gathering of electrons. Now, you understand magnetic fields because you can see those.
Right.
Electric fields are harder to see, but they're analogous. Okay?
Got it. That makes
so,
sense.
Transistors operate on electric fields.
So there will be a buildup of electrons.
Well,
and then
they're actually, yes. And so there is a typical electron transistor has 3 terminals, and the 2 were the typical current flow, and then they have one other, which is the control line. And based on the electric field that is generated on the control line, you'll get current flow or not.
Okay.
Okay. And so you hook all of those in complex ways to make a computer.
Got it. Okay. How hot does air have to be to glow?
Oh, we're talking about almost as hot as the sun. You know, like 5,000 degrees Fahrenheit, something like that.
Yeah.
That's my guess. I don't know for sure.
So does it work in pulses then, similar to lightning, where it's just like sporadic?
Yeah, controlled pulses.
Okay. That also makes sense why it's always hot, is because it's.
And so when they talk about the speed of the processor, what we're talking about is how fast those pulses work all over the circuitry.
Got it.
To make it work.
But don't pulses move at the speed of, or electrons move at the speed of light always?
Okay, so there was one of the very earliest programmers in the U.S. was a woman named Grace Hopper. And she developed a language called COBOL way back in the days back at the beginning. And she gave talks, and I saw her when she was probably in her 80s, and she was at a conference and so she was talking about things like how fast computers work and so on. And she had a 1-foot piece of wire, and she held it up and said, "This is a nanosecond." So that's the speed of electrons in copper.
Got it.
1 nanosecond per foot.
Right.
Okay? So that's an idea of speeds. And so it's not quite, electrons travel faster in a vacuum than they do in materials.
Right. Yep. So how does, why don't they just use copper to conduct the electrons?
Well, they do. All of the chips that are connected to Okay, so you have this piece of silicon with all these circuits really printed on it, and then you have to have a way to get to things other than this chunk of silicon. So they put pads on the outside of it, attach gold wires, and they go to the leads, and the whole thing is in a package of some sort. The leads come out, and the leads, which are probably copper plated with maybe just copper, I don't know. And those are connected to the circuit board. And so there is copper there, but it's complicated enough to make a processor the way without using any copper in it. And adding copper to it would
Only
make
increases
it
the
more
difficulty.
complicated.
Yep.
But some circuits like power switches and things like that may have copper. I don't know. I'm not sure.
Yeah. At some point, that gets from all of silicon and pulses to zeros and ones.
Well, we think of them as zeros and ones because it's conceptually what we like to see, but they're pulses.
Okay, so a pulse is either like
Yes.
on is a 1 and off is a 0?
That's what we define.
Right. Okay. And then how does that make a computer run as you want it to?
Well, first of all, you have to build this circuitry that's going to be the processor.
Yep.
And then you have to connect it to something where you can store a program, which we call memory.
Okay.
And then you load in the memory some patterns of ones and zeros that when you feed to the processor says this pattern of ones and zeros means something. So if you will, memory is just bits.
Right.
Okay?
Yep.
It's ones and zeros. That's all it is.
Yep.
Okay? It's up to the processor to determine what to do with them. So, for instance, we're talking in English. Other people have other languages. So, if you go to France, either the people in France talk English or you have to learn French.
Right.
Okay?
Yep.
Okay, so the processor determines what those bits mean.
Okay. Got it. So what do things like GPU do?
Okay, the GPUs are I'm on thin ice here, so I'll try and say what I know without veering too far off. But basically, particularly in the days when we had the big cathode ray tube displays, the old computer displays.
Yeah.
The way they worked was that they had an electron beam that would scan across the surface of the tube, and the beam would turn on and off, and when it hit the surface of the tube, there was a phosphor, like the stuff that's inside of fluorescent light bulbs, that would light up because it was hit by the electrons. Okay, so you can think of it, they scan across like this, okay? And there was only one electron beam. So they scanned across. Well, so if you want to put, let's say, characters, letters on it, what you have to do is you have to scan across in a two-dimensional pattern to put the dots on in the right place to make it look like a letter.
Right.
Okay. So if you realize if you have the letter A and you have it stored someplace in memory, I don't know where, and you want to see that displayed on a display, you have to take that letter and you have to figure out what dots are going to go in what sequence as this thing is scanning across this way. So you don't scan the letter, you scan across the tube, and you need to slice the letter in pieces in order to put things on the tube.
Right.
Okay. The GPU is responsible for doing all of the grunt work necessary to convert from what you think is text to the dots that appear on the screen.
Got it. So, like, if I type in T, it's the one that translates that into a T I see on the screen.
Yes, typically.
Got it. Okay.
Okay, and of course that's the simplest. If we go to color pictures and we're talking about animations and video, and it obviously gets more complicated, but it's just more of the same.
Yeah.
And so the reason that the GPUs have gotten faster and faster is because of things like video games, which you want to see. You want to see animation going on that is changing all the time.
Right.
Okay. The reason that you can, for instance, watch a video over the internet is because of the fact that on the sending end, they figure out what is really changed from one frame to the next and only send the changes. If they had to send the whole picture every single time, it would take a very high speed internet to do it. So what they do is on the sending end, they say what needs to change, basically send the changes over, and at the receiving end they figures out, oh, only these PR parts need to change, and then display. Okay?
Got it. That makes sense. So they used vacuum tubes and cathode ray tubes.
Well, cathode ray tube is a vacuum tube.
Okay. What did that do?
Well, the cathode ray tube was just a scanning electron beam that lit up the phosphors on the face of the tube. That's what it was.
So, like on the inside of the tube, it
was evacuated. It was a vacuum in there.
Got it.
We call them vacuum tubes.
Right. Yep.
And the reason why we had a vacuum in them was because we didn't want the electrons that were flowing around to be hitting air molecules.
Yep. Because then it would deflect them.
So you got rid of as many air molecules as you could.
And then you would light up on the screen was the phosphorescent. Okay, that makes sense.
Little spots. Now, today's technology is completely different.
Yes, there's no giant tube back here.
Yes, there is. But I had a 21-inch monitor that was a big cathode ray tube. I think it was 45 pounds.
Those old TVs are like a legitimate leg workout to get anywhere.
Yes, correct.
Yeah.
Yes, and that's what they were.
It's a giant vacuum tube.
Yes,
and an electron
right.
scanner.
Yes,
Got it. How does the internet work specifically?
Oh, wow. Okay, the simplest thing is you start out with something here.
Mm-hmm.
In your case, you have a Wi-Fi enabled laptop, which means that it uses radio to talk to an access point. That's what they're called. And the access point does the magic and take the bits that are sent from this end to reassemble them into bits on the other end, send them out over the wire, and this is where we get back to the same thing. Bits are just bits. Somebody has to make meaning out of the bits.
Right.
Okay?
Yep.
And so the internet has defined protocols and processes that allow computers to talk to each other.
Yeah, I was going to say there's got to be at least a common language.
Yes, that's exactly correct. And so there is a common language. And then the very first computers were, the very first internet connection was very, very simple. I think there were 3 computers connected.
Okay.
In the world.
Wow.
3. Okay. And between them, they had a refrigerator-sized box that was taking the stream of bits coming in and trying to make some sense of it and figuring out whether it comes from this guy, whether it should go to that guy or that guy.
Yep.
Okay.
Got it.
So we started there, and there was a lot of learning required because nobody had done that before.
Yep.
And they didn't know what they were getting into. So there are a lot of standards that define this is how you do this thing on this end so that the guy on the other end can get it. And then in the middle, there are all kinds of boxes that are connected to each other that figure out what to do with the stream of bits that's coming and make some sense out of it to say, oh, this goes to there, which goes to there, which goes to the other place.
Right. Okay. Why is a wired connection faster than radio?
Well, because, well, let's just think about a light bulb. If you have a light bulb sitting here, and it's just sitting out here in the middle of the floor, and you start walking out that way toward the mountain, as you go, the light gets dimmer and dimmer. And the reason why is because it spreads in all directions. And the further as you go, the less there's going to be because it's all spread. Okay? So radio has exactly the same issue. Radio is electromagnetic radiation just like light is. It's just that light is magnetic radiation that we can sense with our eyeballs.
Got it.
Okay. So the result is anything that's in the way is going to make it harder for the radio waves to get through.
And air molecules are always in the way.
Yeah, air molecules in the way, walls are in the way. Glass is actually not much of a deal, but for instance, I have a shop out here, and I have an access point in the shop, but I can't put a Wi-Fi connection on the outside of the shop because it is metal walls.
And the metal wall's a turret.
Yeah, and they just basically block the radio waves.
Okay. So how does something like technology that the military uses to find aircraft in the sky, how does something like that work?
That is actually, radar is actually pretty simple in concept. And basically, you just think of it, it works like a searchlight. So it could be a searchlight that actually spreads over a wide area, but it is just like a searchlight. So electromagnetic radiation goes out, hits something, bounces back again, and our eyeballs are the receiver in this case. Mm-hmm. So when the searchlight, and during World War II, the searchlight would be going up trying to spot the airplane, and the way that it would spot it is the reflection on the airplane would come back as light and say, oh, right. That's where the airplane is.
Yep.
Okay. Well, just change the wavelength of the electromagnetic radiation, and you have radar. And so you send out a pulse of electromagnetic, and it hits the metal, and it bounces back again, and you say, oh, the bounce came from there.
Got it. That makes sense. And so something like fiber optic, going back to internet, is just wires.
That's light.
That's light.
Yes, that's light.
Okay.
And so instead of having a pulse of electron go down a wire, you turn on a little tiny light bulb very fast.
So how does that translate into?
Well,
how do they translate that?
At one end, you have what is equivalent to a light bulb, and at the other end, you have something that's sensitive to light.
And then it translates it in the same
into
way
electrical at the far end.
In the same way that you translate electrons.
Yeah, right. Yep.
Okay. What makes something a good conductor of electricity?
It has to do with the atom itself, physics, if we're back to physics. And that is, atoms are conceptualized as a nucleus with a ring of electrons around them, or several rings. And as it turns out, if the outermost ring of the electrons, and this is a concept, I don't know that anybody can prove that this is exactly what it is, but that's the concept. So, depending on the number of neutrons and protons in the nucleus, there are typically the same number of electrons in orbit around as there are protons in the center. So the sun and planets kind of idea.
Yeah.
Okay.
Got it.
But if the outer electrons, think Pluto, is very far off and all by itself, then as it turns out, it is happy to move from one atom to another. And those are the electrons moving.
Got it. And
Okay.
and that changes the material itself.
And so, no, that the material determines whether or not it has outer orbit electrons that are happy to jump.
Okay.
Copper, for instance, has
A lot
electrons that are happy to jump. Gold has electrons that are happy to jump.
but rubber does not.
Rubber does not.
Yeah. Got it. Kind of changing topics. There's been some talk of water-powered or hydrogen-powered engines in the past couple of years. How would something like that work as opposed to a traditional combustion engine?
Well, hydrogen is just another fuel.
It's just
Okay.
easier to find.
Well, hydrogen has some very active chemical properties. Okay.
Like the Hindenburg.
Well, yeah. So hydrogen really likes to have other atoms connected to it. And so, as it turns out, we have this stuff that we use all the time that is made up of hydrogen and oxygen. It's called water.
Mm-hmm.
Okay? And the reason that it's that way is because the hydrogen is really happy to sit alongside an oxygen atom. Two hydrogens with an oxygen.
Got it.
Okay. Now, as it turns out, there is, again, chemistry and physics issue. When you have an oxygen atom floating through the air and two hydrogens see it as a nice complement, when the two of them connect, they give off energy. A lot of energy.
Really?
And that's why you get a Hindenburg. Because it was filled with hydrogen and there was a leak. And
It bonded with a lot of oxygen very quickly.
very quickly, because that is actually what fire is. It is oxygen doing its work very, very fast. That's a fire.
Bonding with
with whatever it can.
carbon.
Yes.
Yeah, okay.
Correct. Uh-huh.
Got
Yes.
it.
Okay.
Okay.
So hydrogen engine, direct hydrogen engine, is just a combustion engine. Okay.
Mm-hmm. Yeah.
The difference is fuel cells. Fuel cells are a way to generate electricity to drive an electric motor.
Yep. Got
Okay.
it. Yep. So there's different kinds of fuel cells though, because there's fuel cells for like a Tesla, and then there's fuel cells for hydrogen,
Teslas
correct?
are batteries.
Got it. Yep.
Okay. There are some hydrogen powered vehicles. But the problem is hydrogen, like in the Hindenburg, you have to deal with very carefully.
Mm-hmm.
And so it's not like gasoline or diesel fuel. You know, diesel fuel, if you've ever dealt with it, is messy.
Yes.
And the reason it's messy is because it doesn't evaporate.
Right.
Gasoline is not as messy because it evaporates quickly.
Yeah.
Okay. But there is a correspondence to that evaporative capability and the energy density. Okay.
That makes sense.
Okay.
Yep.
Okay. Well, the problem is that hydrogen you really don't want to mess with unless you really know what you're doing.
Yep.
And the way that you get a lot of hydrogen is to pump it into a tank under high pressure. Now, do you suppose that there are possible problems with a high pressure tank of hydrogen?
I could see that going poorly, especially if like you get hit.
Yeah.
And
Right.
As any leak is an immediate.
Yes. And so the problem is that although it's pretty high energy density when you get it compressed, you have to spend so much protection around it that the question is, what is the energy density not just of the hydrogen, but of the whole container that you have to keep it in? So if it weighs 10,000 pounds to keep the hydrogen in, then that means your vehicle just becomes 10,000 pounds.
Heavier, yeah. Along with the engine and
the
everything
engine
else.
and all the rest of this stuff, and you probably are trying to transport something, so you have to think about what you call cargo, like this kind of cargo or some other kind of cargo.
Or hay bales or whatever it is, yeah. So is that similar to how a water-powered engine would work? Because I know there's been some prototypes around that.
So, I don't know whether water-powered technology is real or not. Let's just say that. I'm just not sure.
Okay. Interesting. Yeah. Do you think there's a possibility that could happen in the future? Or...
Well, okay, so here's the issue. We can generate hydrogen very simply by applying energy to water. And it will energize the water molecules, and the hydrogen and oxygen will split off.
Yep.
Okay?
Yep.
Well, you have to input energy to make that happen.
That has to come
and that's
from
why
somewhere.
when it goes the other way and they go back together, they give off energy.
Right.
Okay? Well, this is not a perpetual motion machine.
No.
Okay? So if you're going to use the hydrogen for fuel, where are you going to get it from? So if you're going to get it out of the water, what you have to do is you have to put energy into the water.
You have to break apart the water.
Yes.
And
then when it goes back together,
it's very energetic.
It's not going to be 100% energy transfer. So you're going to end up with less energy, I think.
Yeah.
So
eventually you have to fill your car up with water again.
Well, no. The question is, you have to use something else to make the water-powered engine work.
Which would be even more entertaining.
So that's my guess.
Yeah. We're a long way from that at this point.
Yes.
Yeah. How are rocket engines different from a car engine?
How fast they burn their fuel.
Okay. Is that kind of it?
Yeah, that's, as we get beyond the concept, then we're talking about the physics of the flow of fuel and the flow of the burning material and all. Yeah.
But does it run off like a cylinder engine? A cylinder engine?
No. Just it is a straight burn.
Oh, really? So they just...
It's just a straight burn.
So they have like an ignition, some sort of like
Yes.
a lighter, and then they just input fuel.
Lighter. And then they input fuel, but not just fuel. They input also what's called an oxidizer, which is something that is heavy in oxygen. And the two of them go together and they make a big fire.
So do they use hydrogen for that? Because I feel like... Or is hydrogen too unreliable?
Yes, some rockets have used hydrogen. Some rockets have used hydrogen and oxygen, but that's something. My brother John is a rocket engine designer.
At SpaceX, correct?
No, not at SpaceX, but he may do some work for them. I don't know, but he would be able to answer those questions much better than I can.
Yeah. Well, at some point I'll have to see if he's willing to come on the show.
Yeah.
Would it be possible to use a rocket type engine for a car?
Well, actually, back in the 50s, there were two companies, I think GM and Chrysler, tried to build cars with what I would call jet engines.
That sounds exciting.
And it was actually what's called a gas turbine, which is it doesn't just use the thrust, but it drives a shaft. They could drive something. Didn't really go anywhere.
No.
But if you're talking about trying to go very fast on Bonneville salt flats out in Utah, yes, I believe there's a rocket-powered car.
Yeah.
But
not really useful.
Rocket-powered vehicle.
Yes.
Okay.
Yeah. Not really useful for getting around town.
No, I don't think so.
So, a rocket engine is more efficient, though, correct?
Different.
Is it just different?
Yeah.
Okay. How does an electric battery work as far as charging and powering a car?
It's purely chemistry.
Meaning?
It's just where are the electrons and how do you get them to stay someplace and move someplace else when you want them to. So when a battery is charged, you've got a bunch of electrons sitting somewhere. When you're using the charge on the battery, what that means is you're allowing the electrons to move from one place to another.
Right.
Instead of doing it the way the lightning does,
where it's just
think of a gigantic wire between the cloud and the ground with a switch on it. So the electrons can move when you want them to.
right.
Okay?
Yes.
So battery is electrons stored someplace, and you let them move to another place that they would rather be.
So somewhat similar to like an electron field, or no?
Do you know what static electricity is?
I've felt its effects.
Okay, yes. Okay, so for instance, if you take a balloon and rub it on your hair, you can make it stick to the wall.
Right.
Okay, so what you've done is when you've done that rubbing, is that you have moved a bunch of electrons on the surface of the balloon. And rubber is an insulator, and so they just sit there. And so when you put them up against the wall, the electrostatic forces of the electrons in one place and the wall in the other place make the two of them say, oh, that's nice to be near each other.
Why?
Because just the electrons don't. Let's see. Let's
Electrons are needy.
Well,
they want a friend.
Well, think of it this way: if you have a water tower, you pump water up into the water tower. The water actually doesn't want to stay there. It wants to
because of gravity.
It wants to go down because of gravity.
Lots of kinetic energy.
So it's just a force which wants to move someplace else, and if you open a pipe, then it'll flow. So if you get electrons away from the atoms that they were part of, then they're going to want to go back.
Right. That makes sense. So, charging a why would it not then be possible to collect the electrons from a lightning strike?
Well, in the fantasy movie, what was it called? They actually do collect them, but no, it would be very hard to do that. I don't know how you could get them to actually go into a container and stay there.
Because it's such a rapid input of electrons.
Well, you have to think about what is actually happening on the level of a physical atom. Okay, and it's if you were able to grab an electron off of an atom and put it someplace else, it's going to want to go back there.
Because it's why?
Because that's the way atoms are.
Easy as that.
I mean,
Yeah.
they're going to want their electrons back.
Yeah. Huh.
I mean, in a way, that's the way God designed it.
Yep.
Okay, that's why.
That's why. It's just because that's how they do it. Huh. Fascinating. So the electrons want to go back up to the cloud, and that's the reason that we can't. It's so hard to store them.
Well, no, they're in the cloud, and they got in the cloud because a stream of air is blowing through the cloud, moving the electrons from one place to another.
Got it.
And so there are two kinds of electron of lightnings. One of them is cloud to ground, and one of them is cloud to cloud.
Right.
And cloud to cloud, you move the electrons from this cloud to that cloud, and they want to go back to the cloud they came from.
When the lightning strikes the ground, though, it is the electrons now in the ground, in the earth, would like to go back to the cloud, or are they happy where they are at this point?
I don't know exactly.
Okay. Well, sometime I'll ask a lightning expert. I don't know if there are such things, but
Yes,
I'll see if I can find one.
probably are.
There probably are. Is nanotechnology possible?
Yes.
To the extent of...
Have you heard of carbon fiber?
Yes, but I don't even know exactly what it is.
That is carbon atoms arranged in a lattice, which you think, if you go down to the building supply, you can get lattices.
Like this chair a little bit.
Yeah, like that. Yeah, that's okay. It's mostly two-dimensional. This is really three, but
Right.
it's two-dimensional. And so what you do is you have a very thin sheet of carbon atoms connected to each other. And then you roll them into a tube. And if you do that, you can do some amazing things with them. And so all of the fancy cars that have very strong, very light bodywork, that's built out of carbon nanotubes.
And that does come at the cost of, it's now brittle.
Expensive.
It's expensive, but also brittle, correct?
I don't know what the characteristics of the tubes are. They're pretty strong, I know that.
Yeah. Yeah, I've seen carbon, and carbon fiber is hailed as this great technology
magnetic, magic material. There's no question about that.
Yeah, that's pretty wild.
Light and strong.
How are, I don't know, I was just thinking, as far as could you have a container of, I don't know what it is, but some sort of robots or something that would be able to expand themselves?
Try to expand on in your discussion.
Yeah. For instance, if you had a small robot that was able to expand itself and connect with other robots and then change its form. Is that kind of thing possible, or does it merely live in Marvel movies?
Well, other than science fiction movies, I don't. I don't think so, because what you're really talking about is an object that could merge into another object and make a bigger object.
Yep.
You know, we can see the opposite of that at the cellular level when cells divide.
Mm-hmm.
But even cells, I don't think, merge.
No, but they do come together to build a structure.
That's entirely. That's That's. But a cell is a very complex thing.
Mm-hmm.
Very complex.
Right.
And so when you talk about something like a carbon nanotube, you're not talking about the same universe.
It's so much simpler.
Yeah. Carbon nanotube is just carbons. In a cell are nanomachines. And that makes it a wholly different, The surface of a cell is a complex collection of cells, of molecules in a particular orientation that will let some materials flow through and some not. I mean, this is... And inside there's all these nanomachines doing things.
Is that ever possible with programmable electronics?
At that level? I don't think so.
Not yet, at least. Not for a long time coming.
There is an amazing book. Oh, I wish I could remember it. Which talks about the complexity of the cell. And for instance, a bacteria has a cellular outside, and then it has little flagella which stick out from the surface. And they are driven by molecular motors that can go forward or backward.
I think I was watching something about that the other day, and it's like it's so
just
much more efficient than like a car engine.
Well, it's
with a drivetrain.
Amazingly efficient and complex and nano-sized.
Infinitesimally small. Yeah.
Yes.
Yeah.
And so,
Pretty crazy stuff.
Yes, it is. Yes, it is.
How are airplanes able to fly, given that they weigh so much? These are just all the questions
why
I've
do
had.
boats float? They're made out
boats
of metal.
float, but because of water displacement. But air is much lighter than water.
It is, and yes, and so if you have you ever driven down the road and seen a convertible driving by you, next to you,
Mm-hmm.
and the fabric on the top of the convertible is bowed up.
Bowed up meaning
Meaning not flat on the surface, but it looks like it's up off the surface of the, yes.
Yeah.
Okay.
Yeah.
Okay. That's why an airplane flies.
Is because it's going
Okay.
fast enough there.
No, okay. So no, it isn't fast enough. The trick is if you have a wing and it's shaped like this, the body roughly The bottom is flat and the top is curved.
Okay.
Okay.
Yep.
So you have a stream of air that is coming up to it. And the number of molecules on this side and their placement all around, when it goes to the back side of the wing, has to be the same. Okay.
Which means some molecules have to move faster than others.
Right. The ones over the top have to go faster. And
Yep.
the only way they can do that, if you have the same amount on this side and the same amount on that side, is for them to be spaced out from each other. Not just going faster, but spacing is different.
So similar to, like, there's almost a vacuum.
Exactly. That's what it does. There's a vacuum over the wing, and it's sucked into the air.
Aha. But that is also because of speed, correct?
Yeah, it depends on the shape of the wing and the speed of the airplane and all the other stuff. But the concept is not changed.
So if you were to design a car that was concave instead of convex, would you?
You have to think about it.
Pull itself
not just. Well, yes, that's why, as a matter of fact, they have wings on the back of race cars, is to push it down.
But that's the wing is like.
Yes, and that is correct, and it provides force because it's an upside down wing, so it's been sucking it down.
Huh. That's why that works.
Yeah, it's an upside down wing. Concept doesn't change.
Huh. So there is a speed that it has to hit, though, in order for that to happen, correct?
Well, yeah, actually, when you have one of those race cars going, they have to be going pretty fast to generate a lot of downforce, but that's when you want them to do it.
Right.
It doesn't really matter when they're going 5 miles an hour, or even if they're doing 60.
So when an airplane is descending, it's slowing down?
Yeah, it's slowing down, and obviously the lift on the airplane is going to change as the speed goes down.
Right.
But what they do is the airplanes are designed for cruise speed and altitude.
Yes.
So they want the airfoil, the shape of the wing, to make the maximum lift and the minimum drag, which is the force when you push those air molecules apart. It takes energy to do that.
Right.
Okay, so you design the wing for the altitude and the speed that you expect the airplane to be going.
Got it.
And it's going to be less efficient at lower or higher, different speeds.
Fascinating. So how's an engine on an airplane different than like an engine for a jet or a car?
Well, the engines on airplanes are jets, typically.
But they're not shooting. I mean, it's not a rocket engine.
No. Okay. So obviously the first airplanes all had propellers, right?
Right.
Okay. And then they experimented with rocket aircrafts, and the problem with that is that they are not fuel efficient.
No, I can imagine.
Yes, okay. So then they went to jet engines where the thrust is provided by the burning air out the tail.
Got it.
Okay.
So similar to a
Yeah,
rocket
that's what
engine.
it is. It's the thrust, but that.
Okay.
But that's not what today's jet engines go.
No.
They, in fact, are what's called fan jets, which means they have very special propellers inside.
Mm-hmm.
And so if you look at the front end of a jet engine today and you see those little blades,
Yep.
they're a fan.
Right.
The fan is a propeller. So what happens is it uses both the thrust of the jet and the thrust of the air flowing through from the propeller.
to
generate the thrust that pushes.
Got it. How did the original planes with like those tiny prop propellers on the front gain enough?
Well, you just need to get the air moving enough to screw your way through it, if you will.
Okay. So like legitimately climbing your way into.
Yeah, right. You just push the air back, and pushing the air back, put thrust. So keep pushing the air back, and you move forward.
And that also sends the air into the wings.
Yes, that's correct.
Okay, that makes sense.
Yeah.
Your dad invented the microwave.
Oven.
The microwave oven. What's the story there?
During the Second World War, radars were invented. The story goes that some guy stood in front of a radar antenna when it was in operation and noticed that he was warming up. Honestly. Now, I don't know whether that's a true story or
yeah.
But obviously, maybe microwaves can be used for something other than radar.
And
they can.
Yeah.
As a matter of fact, what happens is that the frequency of the microwave generation in the tubes and the ovens resonates with water molecules. And it makes the water molecules jump around and they get hot.
Huh. That's wild. So does a microwave oven cause any damage to the food inside of it because of the electrons?
I don't know whether this is a philosophical question. No, I mean that. Whether, obviously it does something.
Right.
It makes the molecules resonate. And one of the things that you can tell about microwaves, if you've ever put something frozen in a big frozen thing in a microwave oven, you'll notice that it gets real hot from the surface.
And not super hot in the middle.
Not super hot in the middle. And so microwave ovens are not really good at heating something that is a lot of bulk, because the waves only go into the surface a certain distance. And after that, then the way that the heat travels to the rest of it is the same as a regular oven.
Okay.
So it's just the heat
sense.
that's out here works its way through the materials. And so that's why if you put something that's thin in a microwave oven, it heats up real fast. If you put something that's thick in a microwave oven, the surfaces heat up fast, but then you have to wait for the middle to get warm.
Yeah. As we kind of wrap up here, I always like to ask, what's your best piece of advice?
Love God with all your heart.
It's a pretty good one. Thanks for coming on the show, Grandpa.
Okay.
It was lots of fun. I learned a lot.
Okay,
and,
thanks.
Through a bunch of random questions that I had no idea how anything worked, and now I have
some idea.
a tiny more idea than I did.
Oh, so, that's great. Thanks very much. Okay.
Thanks, guys. See ya.
Yeah, bye.
Add a little.